This is my first of several introductions to eigenvalues and eigenvectors, and I'm beginning with the definition and some examples. So from our textbook on page 269, we're given the following definition. Given a matrix A, a number lambda is called an eigenvalue. We just underline it. It's called an eigenvalue of A if there is a non-zero vector V for which A times V, and so here's A times V, V is expanded to xy, is just lambda times xy. And this is saying that if I multiply some vector by the matrix A, all I end up doing is I end up stretching it. Lambda is a constant, and lambda times V will be a vector in the same direction as V. But if lambda is bigger than 1, it is going to be longer than V, and if it's smaller than 1, it'll be shorter than V, and if lambda is negative, it will be in the opposite direction of V. The vector V is called an eigenvector corresponding to the eigenvalue lambda. Let me show you a couple of examples, and again, similar or the same as what you're seeing in the textbook. Let's let our matrix A be this. I'm going to change color. 1 second. Here's our matrix A, 4, 3, minus 1, 0. In general, if I pick, well, I'm going to pick one that does have an eigenvalue, and so 6 minus 2. If I multiply A by 6 minus 2, I get the 4 times the 6 is 24, and the 3 times the minus 2 is a negative 6, and I end up with 24 minus 6, and that's going to be 18. Minus 1 times 6 gives me a minus 6, and 0 times minus 2 is a 0. So this is my result. And I can factor a 3 from here, and I get 6 minus 2, and I see that multiplying this matrix by the vector 6 minus 2 has a resultant of a new vector that is just 3 units times 6 minus 2, so it is stretched 6 minus 2. Minus 3 would be an example of an eigenvalue, and the eigenvector, corresponding eigenvector, would be 6 minus 2. And we're going to talk about where we find these values. It turns out that any scalar multiple of 6 minus 2 is also an eigenvector corresponding to lambda equals to 3. So for example, let's do it again. In place of 6 minus 2, let's work with minus 3, 1. I've just divided 6 minus 2 by negative 2. And I claim that I will end up with 3 times minus 3, 1. I should end up with a minus 9, 3. Let's see. I get a 4 times a minus 3, which is a negative 12. And a 3 times a 1, which is a 3. I get a minus 1 times a minus 3, which is a positive 3, and a 0 times a 1. So that's my result, which is just negative 9, 3, and again, that's just 3 times minus 3, 1. Lambda lambda is equal to 3 is the eigenvalue. In this case, there's a different eigenvector, minus 3, 1. And so eigenvectors come in many shapes, all scalar multiples of one another, but the eigenvalue is specific. And so there'll be a whole line of vectors that when multiplied by A will be stretched by 3 units by that eigenvalue. Just to show that that's not true of all situations, let's just take one more example. 4, 3, minus 1, 0. If I multiply this by 1, 1, for example, I will get a 7 minus 1. And this is not a scalar multiple. There's nothing I can multiply 1, 1 by. There's no scalar lambda that I can multiply 1, 1 by to get 7 minus 1. So in general, when you pick a vector, that vector is not an eigenvector. And so the next part of this, I'm going to talk about how we find these eigenvectors and eigenvalues. Thank you.